Okay. Now we are leaving YouTube. So I'm presenting Annette. She studied chemistry at Marburg, Germany, and she finished her diploma in 2006. Then she obtained a PhD in chemistry in mines at the Max Planck Institute for Polymer Research in 2010. Her thesis was focused on dextran-based hydrogels for sensing and cell growth. Later on, she came to Buenos Aires to do a postdoc with Omar and Gallo at CENEA, working really hard and also really smart, I saw her, on polymer functionalized and gated nanopores. She came back to Germany and obtained a position as assistant professor in the Technical University of Darmstadt, Germany. There, she's now full professor and the head of the research group Macromolecular Chemistry, Smart Membranes in the Department of Chemistry. Annette received many awards within the last year, such as the ERC Starting Grant, which is very competitive in Europe, the Exploration Grant of the Beringer Ingelheim Foundation, the ADUC Award for Junior Research Group Leaders in Chemistry in Germany, among many others. Finally, she was mentioned Outstanding Reviewer for Matter Horizons and Nanoscale Horizons for 2 years in a row, and was invited as keynote speaker in several important conferences, such as the UPAC Polycar in 2020. And we are very excited to have Annette here, and we thank Annette in advance for joining the seminar. And now I leave you all in her hands.
Yeah, thank you very much, Yanni. It's the pleasure and the honor is actually fully on my side, and it's really, really nice to see you all again. And I already now like the Zoom formats for this, as it's true that in the last 10 years, not only professionally some things were happening and finally leading to a permanent position, but as well in the private life and with small kids, as many of you might know, traveling is a little more restricted. In addition to COVID, which now kills everything, but that's another story. So what I like to do in the last minutes, I was thinking about what to present, and I finally decided to focus a little bit on the polymer functionalization and especially on pushing the limits of this, as I think this is maybe complementary to what many of you are doing, and yeah, we can find a lot of connection points via this. But let's start for those who don't know where is Darmstadt, and that's not a problem, because even when I tried to apply here, I remember the moment when I saw this position, the first assistant professorship when I was in Argentina. I did not feel at all ready for such a position, but I was just going to tell this to Omar and Gallo, because the title was just basically my postdoc. And of course they told me, well, don't hesitate, apply, and you know what came out of this. So Darmstadt is really close to Frankfurt. You see this here on the map. So if you at any point travel to Frankfurt Airport, just let me know. We are just 30 minutes away. There's just a triangle of Frankfurt, Mainz, and Darmstadt around the airport. And as I try to give a little bit of a story, I realized that, okay, it's already 10 years that I was traveling from Mainz, which is just next door to Darmstadt, to Buenos Aires to start my postdoc, because I met these two smart guys, one in Mainz already, Omar, and one then in Buenos Aires. And this was basically the kickoff of everything that happened afterwards. And I was just realizing I'm missing a group picture. Now I have the group picture. Thank you very much. After this postdoc, I was coming back, and that's where we are now. So to advertise Darmstadt a little bit, in case you want to escape Buenos Aires to something green and much more smaller, you are very welcome. So this is the Campus Lichtwiese, where the chemistry department is located. This is actually the chemistry department. This is the Zoom on the chemistry department. I'm currently located over here in the first floor, giving my talk in Buenos Aires. And you see here the city starting, so it's a really nice place. And on the other side, the Odenwald is starting, so purely nature. And yeah, this is what was developing, and these are the people that did the work in the lab that I will present. This is my second generation of PhDs. They are all of them finished, not yet all of them defended. I'm waiting for some PhD thesis on my table, but publications all out. And this is now the third generation. And I think this picture was taken in 2018. So how did the journey start? Actually, it started in Buenos Aires because the task of my postdoc that Galo and Omar were giving me is take these mesopores. At that time, I had no clue about ceramic mesoporous material, really no clue. So thanks to all of those who introduced me into that topic, we are still using these as working horses. And combine this with polymers. I had some ideas about polymers at that time. And the first challenge in the lab was, okay, try to build the Schlenk line, because this is necessary to do these polymers, otherwise it will not work. Assemble it, it was there, and bring it to work. And this is not the Schlenk line from Buenos Aires, this is the one from our lab now, but it looks similar. I don't know if it's still there. But this was my very, very first shock at that time. Imagine you're in a different country, you're completely new to a research group. The first thing after assembling such a thing, and there was only one, that happens is applying vacuum and it's falling apart, but completely. This was a Friday. And I still have this shock in my mind. And thanks to some guys over there. Thanks, Andres. I don't know if you're there, I don't see you. But he saved my Schlenk, and I learned that you can use polarized light to see tensions in glass, and then you can convince the glass blower that actually has to do an additional temperature treatment. So I learned a lot, among others, this. So this was the starting point, and the question at that time was, how can we switch or gate nanopores? And this is just one example. That we did, we tried to use already at that time these phosphate-containing polymers, polymerized in a radical polymerization, and then measuring cyclic voltammetry. And I think most of you are familiar with this. What you do is that you try to detect this model redox active compounds at an ITO electrode, which is located below this mesoporous film. So in case the pores allow these molecules to pass through, you can detect them, and then you detect the current, and this gives this kind of signal. So what you would expect is, because you have pores that are so small that they are in the range of the device screening length, that if you switch on the pH to a negative charge, that you can electrostatically exclude the identically charged molecule from that pore. And in that case, you would see no or almost no current, and this is this red curve. I think even at that time that was already known, but what was the question here is, can we do this more specifically using, for example, calcium? Because you would expect as a chemist that this calcium ion is neutralizing this phosphate, and then the pore intuitively should be neutral and molecules should pass again towards the electrode, and this is actually what you observe. Well, being fair, you have to say that's not selective to calcium, that's probably selective to two valent ions, but nevertheless, I think this was one of the examples showing this selectivity and this interaction with ions. So till now, I think there's almost every trigger that you can imagine. Magnetic field, I don't know, but all the others, I think they are published. But still, there's a lot still going on in terms of ion binding, and I will come to some of these examples as well. So starting from this point of combining light-initiated or induced polymerizations in pores, what draw my attention and which I take as a challenge, if you look at these biomolecules, they are much, much more complex than just having a charge switching on and off. And I like this picture a lot, because what you see here in the different color codes are negatively charged regions of the potassium channel, more hydrophobic or unpolar, more polar regions, and as well, not only a distribution of functions or surface effects or forces, but as well of size, because you see a selectivity center very small here. And then if you look at theoretical work, and this is one work from the group of Igal, which I think most of you know as well, from 2017, which I like a lot as well. And please just look at the scales here. He demonstrated how to direct transport in nanopores by using two orthogonal polymer gates, basically. If you switch on one, molecules are passing, you close it, you change the stimuli, you open the other one, so you get a kind of directed transport. And he just showed that this would work in his simulation if you have a kind of polymer like this one. So hydrophobic, 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 you can count the monomers, and then negatively charged, hydrophobic or unpolar, negatively charged. Well, I don't know any polymer chemist who is able to design this, not the sequence and not the local resolution. So this is very much what we had in mind. How can we push the limits of polymer functionalization? Can we get more local? Can we get more control on the sequences of polymers? Well, this maybe you need peptide synthesis, but how far can you go by using classical polymerizations? So these are the questions that we are asking, and what's behind in terms of transport are questions like, can you direct transport through such systems? How small do you have to get to do this? Can you be more selective? And of course, understand the confinement effects. So I tried to organize my talk because Yanni told me I can use 45 minutes. That's perfectly fine. So it's at some time you get bored, just let me know. I can skip parts. But I will try with polymerization control to then go to a topic that we started in the context of doing step gradients, functional templates, and nano-local placement of functional units. So this, you know, I can possibly skip this, but just to give you the context, the two working horses we are using is still the classical Peronic recipe of Mesoporous silica films. And we discovered a second one because at some point we were just looking for slightly larger pores. And this is taken from this literature reference. The same recipe, but just swelling the micelles a little bit, so slightly larger pores. And everything that I will discuss is silica-based. So when we started in Darmstadt and in Buenos Aires, I used mainly free radical polymerizations. And there's a lot of literature as well from Omar, which you know, on ATRP. So when we started thinking about control, we thought, okay, if you use ATRP and you're a polymer chemist, you know that there are a lot of components involved in getting the equilibrium. And we thought, okay, having all this in pores and really looking at control might be challenging at these pore sizes. So why not taking another polymerization mechanism? And in addition, we wanted something with light, ideally, because we already had some more ideas on nanolocal control. So we needed light. So what we use a lot is this Iniferter initial polymerization. You just need one molecule. It's asymmetric. This is called R group and Z group. You initiate, you split this bond here, and then you can get a controlled polymerization because this part is adding the monomers and this is terminating the reaction, and you can get a kind of equilibrium as well. Maybe a little less controlled than ATRP, but that should be okay for us. We played around a lot with different monomers. So we did Twitter ionic ones. I will not that much talk about this today. We were looking at PMAP because of the two pKa values. We used PDIMA, polymetac, because that's a strong polyelectrolyte, and you can just nicely track charge density if charge is not pH responsive. And in the first step, and this is a little bit, the repetition or the proof that this polymerization itself works, and this is what we showed with Galo together for the free radical as well, is that you can control polymer amount in these porous materials. This is an IR spectrum. And if we use these kind of polymers, you have this CO vibrational band, and you can nicely track this in the IR spectra. And you can do ellipsometry, and then as well, you get the refractive index. You can translate this using effective medium theory as well, something I learned in Buenos Aires, into the free pore volume or the filled or the filling degree of the pores. And you see that you can control polymer amount and you can control pore filling with these, and you can even achieve, according to ellipsometry, pretty high pore filling degrees. So if you do this control and then you look at the transport, the same measurement that I showed you before. So you have an electrode below the Mesoporous film and you measure the molecule here that's arriving at the electrode. And this is actually data from a free radical polymerization with the work of Gallo. We published in 2015. You see that with polymerization time, you increase the polymer amount. And if you take a strong polyelectrolyte, this results in increasing ion concentration inside these pores. And this was, you go from a silano-regulated to a polymer, fully polymer-regulated pore. And the results for this Iniferter polymerization look quite similar. So this depends on the polymer amount and the pore filling. And I think Igal for this system did the simulations. And what is nice about this data, especially if you look here, for the chain links of 5 monomers per Iniferter or per initiator, that you still see the effect of the silica wall. You nicely see the anion, so the counter ion distribution along the polymer. And this already gives the indication that although the spore radius is so small, you have no homogeneous distribution of charges, of pH, of whatever. So what I think experimentally is fully missing right now at these scales is to get insight or direct measurement of what happens here along the pore radius. So you need this theory to approach this knowledge. And this is then one thing that as well was inspired by a work of Omar on planar surfaces. He used these strong polyelectrolytes and he just changed the counter ions. And if you think on transport and membranes, we thought, okay, how can we go one step further to real applications, although we are still far away, because in real applications, you will never measure cyclic voltammetry in a pure 100 millimolar KCl solution. So our first question was, okay, if we change the ions, what happens? We knew this work from Omar I think in Cambridge at that time, that he could change the wettability of the surface from hydrophilic to hydrophobic just by changing the ion and the polymer conformation. And we knew work from a colleague here in Darmstadt who's doing MD simulations, and they are looking a lot into LCST behavior and ion influences. So you have contact ion pairs, water-mediated ion pairs, and everything changes, basically everything. So we were just asking the question, okay, can we have a correlation? Can we reproduce this wettability that Omar saw on planar surfaces? And what does this do with the transport? And this is the result. So you can go by using chloride, which is the usual cyclic voltammetry condition. This is the advancing and the receding contact angle that we measure. And if you use this perfluorinated ions, you have like almost 90-degree contact angle by doing nothing, just changing the ion in the solution. And very interestingly, if you then measure cyclic voltammetry and basically you just change the ion of the supporting electrolyte, you can basically go from normal transport to almost ion exclusion. And through this, we contacted Gallo and Estefania at that time. And it was very interesting. And Estefania, sorry, I saw that you are there. I think it's very briefly what I say about these results. So the main conclusion, I think, was that this is ligand binding driven. So if you have strong ligand binding between your ion and the polymetallic, you will mainly see this effect and then the hydrophobicity and not the transport. So that you have a competition between the transport of the ion that you want to transport and detect and the ion that is actually in addition given to that solution. So message here is you have to consider what is in solution and not only what you have to transport. So continuing with this, one big question in this polymerization part was that I was always getting by reviewers, depending on which community you are. Of course, it's the molecular weight. Well, that's very challenging. And second is, how do you know that it's homogeneously distributed? So I was always arguing like, okay, of course, you have the transport. So if you would have pure silica, your transport would look differently. But this is, of course, everything indirect. And we were working a long time on getting this EDX scanning. And still it's a challenge, but for this sample, we got it. And what you basically see here is a TEM cross-section of such a sample. And then after polymer functionalization, the elemental map, in this case, we just plotted phosphor and sulfur. So you see that your initiator, here the sulfur in blue, is still present in the pores after doing a polymerization, and the phosphor is present as well. So there are green dots and blue dots here in the cross section. And this is a good indication that in terms of control, you may be able to reinitiate the polymerization. And this was something that we wanted to do for a long time. So based on these results, we thought about a system taking our Iniferter, first in a first step polymerizing DMR-EMR, not to a full pore filling, and then repolymerize the pH-dependent negatively charged phosphate monomer. And the aim was to get somehow a similar distribution, because the question was if the chain architecture influences the transport. And if you know about the work, I don't have it in this presentation, but I think Omar has an early paper on that, is having a Zwitter ionic pore. And intuitively you would say, okay, if it's Zwitter ionic, so every monomer has a positive and a negative charge, that's just neutral. But what you observe apparently, and we saw this in one example too, is that you get a so-called bipolar pore. So no ion likes to enter this pore at all. So our question was, can we do such a system? We have these positive and negative charges in approximately the same ratio too. And does this then show as well a bipolar pore? And what we observed is in this system that, okay, first the synthesis results, of course, you track the infrared spectra. You see the increase in the infrared band for the second polymerization step. That's already a good indication that it worked. And you see this in the pore filling from ellipsometry as well. And in this case, we used both porous systems. And so the reinitiation is possible and the block copolymer formation is probable. And then looking at the transport here, you see the pH against the current density, again, extracted from cyclic voltammetry measurements. And what you see is that you have an anion selective region and a cation selective region. And the interesting one is here. And it's not, at least in our experiment for these samples, not showing ion exclusion, so no bipolar pore, but more or less a gradual transition. So our conclusion from this was, at least for this specific system, that the chain architecture has an influence, and to get these bipolar pores, apparently you need this positive and negative charge combined into each monomer. So this was the first part on control. So continuing basically more the postdoc idea into getting more control using Iniferter initiated polymerizations. And from this, we had one more question, just remembering this nice image, is how can we get the local control into the systems, and not just local control in terms of structure, but especially in terms of functionalization. So for this, we were just following two strategies, and I like to start with the first one. And the first one is about building up layer-wise local control. And then, of course, you can think about co-condensation. And we started with just looking at the film preparation, and what you know all, I think, is this part. This is classical dip coating, evaporation-induced self-assembly. What you see is the film thickness in black, the refractive index in blue, and this is basically just a reproduction of what I think Grosso and Faustina were publishing in Chem Matter. You see first with increasing withdrawal speed, a reduction of film thickness, and then again an increase. And basically this is due to the viscosic draining regime and the capillary regime here. And usually I think you're over here, and yet then you can nicely tune the film thickness. So we were trying, because here you always have these rim effects, I think you know this, to use gravure printing. The disadvantage of this is if you have these this wafer substrates and you do not just tune your equipment a little bit, they are breaking easily because you're pressing on them. But the films look very nice, and you can just tune the film thickness from very small film thicknesses to, let's say, 120 nanometers. Refractive indices look nice. And the advantage of this now is that if you want to build multi-layer films, the contact of the second, third, and so on layer with the below layer in terms of a liquid state is much shorter. because you transfer much less volume and you just do not dip your sample for a long time into the salt solution. And we thought this is maybe advantageous to avoid just like problems with infiltration or something like this. So this was the motivation behind trying gravure printing. And the idea then was, okay, if we want to do this layer-wise buildup, we have these nice polymers already that are just doing our micelles and our mesopores here. And then we just waste them. We just throw them away by burning them out. So if we can do polymer chemistry, why not designing these copolymers in a way that they are doing micelles? We are not that much interested in getting a perfect ordered structure. If it's accessible, that's fine. And then designing them in a way that they already carry the function that you want to control transport. And this is what we call the functional template. So the first candidate, we were just screening literature a little bit to see which polymers would do micelles in a range that could be suitable and have some pH responsive block. So this was our starting point. And the first candidate is shown here. This carries a carboxyl group if you deprotect it. And we just introduced this into the salt gel chemistry, and then we did the same, the normal protocol of temperature treatment. Of course, not 350, but 200, I think, if I remember correctly, and then just measure transport. So yeah, as you see here, the SEM images look okay. The TM images are not perfect, but okay, indicates a kind of a nanoscale porous structure. The IR looks nice because you can find your polymer. So the question then, of course, is what about the transport? And of course, you have very highly filled pores. So you need electrostatic attraction to get something in there. But if you have electrostatic attraction, so the negatively charged carboxylic group at basic pH, the positively charged test molecules, the ruthenium hexaamino complexes, go in. And if you have seen a lot of CVs, this shape already indicates that there is not a lot of space moving in these pores. And if now you build this 2-layer film and you do just a normal mesoporous silica film on top and you chemically extract that template, you see that there's in principle, not a lot changes, but you see a kind of effect of a second layer. So I'm not sure that I can state on really the effects of building 2-layer, 3-layer films. I think that's a bit too early. We do not have that systematic data. But what you see clearly is that you see the functional template. You see in the CV already as well that you have highly filled pores, and yeah, that we have a kind of proof of concept. And then we thought about going a step further, because ideally you not just want something entrapped inside these pores, but our first idea was, and I think now I would say it was a bit naive as well, but it was a nice idea, to get an end functionalization that chemically reacts in the salt gel with a silica formation. So get a silane group here. This is a lot of chemistry, and we did this in collaboration. The second idea was that, of course, after that, you want to destroy the hydrophobic block to get some pore space in the center. So this was my idea, quite schematic. Then I was just, because this was even too much for my synthesis skills, I was talking to colleagues that are really in the block copolymer and anionic polymerization business, and he came up with an idea. And the idea, the polymer was this one. So you have a silane group at the end, you have an hydrophobic block, and you have this metallopolymer in there. So these are, for the people that are doing metallopolymers, they are quite precious, they are quite expensive, they are quite hard to synthesize, but you can nicely destroy them with HCl. Don't tell anybody in that community to do that, but I was interested in doing that, so we just tried. So we had a joint master thesis, and this candidate later joined my group as a PhD. Now she is already finished. It took some time to publish this data. But this is the synthesis, and as I said, it's even beyond my knowledge, so hopefully don't ask me too much details, but just to show this, we did these metalloblock copolymers. This is the synthesis, and as a reference sample, we did the PS PVP with a silane end group. These are the electron microscopy images. So here you see that, of course, if you do anionic and control polymerization, you can change the block length. We did the PSB PVP with the silane end group. And then here a different composition. And here again, a different composition. And then we did this with the PFS, so the metalloblock copolymer. And you see that, yeah, maybe structure again is not that perfect, but it indicates that there is a kind of a nanoscale space in these materials. And this was already a good hope that we can measure transport. And what we did as the first thing is to look at these candidates. And if you have them inside the pores, their pores are, of course, blocked. So this was a good news for us, because this tells you maybe you do not have a perfect structure, but at least you do not have large cracks, because then you would see some transport through these cracks. And if then you burn out this polymer, you see what you would expect to see from silica. And this as well is a good news. So this indicates that you can electrostatically close the pores, and so they should be quite small. And based on this, we were then just looking at the metalloblock copolymers after extracting the metalloblock part. So there's just the PVP left. This is pH responsive, so pKa around 4.5, you can get a positive charge. And this is what you actually see here, that at acidic pH, the negatively charged molecules like to go in here. The positives do not like to go in there because of wettability and charge combined effects. And if you go above the pKa again, you always do not have a lot of transport. And if you switch this back and forth, and this as well as an indication, I would say, for the highly filled pores, you can switch between 9 and 3, but you still see an increase going on here from cycle to cycle. So there's a slow process as well going on in these pores. So this part, I think we had two systems, and now we have in the ERC project, we have one PhD student trying to continue this. I think she has 4 polymers in the pipeline, screening different responsivities and continuing this part. And the aim is then to build up more complex architectures and go towards this hierarchical build-up and investigate how the architecture plays a role on the transport too. So in the last part of the talk, and actually I did not follow the time, I hope I still have 10 minutes, I'd like to start a last concept, again going into this direction. And this is an idea that I already discussed, I don't know, Galo, if you remember, with you when I applied in Darmstadt. This was one of the very new ideas that I had, combining my expertise in surface plasma and spectroscopy just for characterization with the polymerizations, because I said, okay, this is somehow light, it should initiate a polymerization. And if you know a little bit about surface plasmons, this is light that is nanoscopically confined. And I have to start a little bit earlier, and this is the relation to wetting, because beyond this nanoscopic light, you can as well play with these interfacial effects that you have in pores. And to understand this, you have to understand what's a wetting transition, what I call a wetting transition. And just to show you that you can just design a porous surface such that water does not like to penetrate because the contact angle is just too high. You can maybe compare this to a kind of Cassie wetting state. So if then you change the contact angle below this transition contact angle, and I mean, intuitively you would say, or you learn in the lectures that 90 degrees is the transition from water imbibition to water exclusion. I think in these pores, it's a little bit smaller. It's around 75, maybe 70 to 80. But if you change the polarity along this transition, so slightly below, let's say 70, you get water imbibition. And what we did just using spiropyrene, if you irradiate this, you get this myrocyanine form. It's more polar. And if you tune the initial contact angle such that you're just slightly above this transition contact angle, and then the small change in the polarity is sufficient to cross this transition contact angle, you get water imbibition. And if you use droplets, it's just playing around. If you use droplets and place them close enough, you get at the same time droplet coalescence, because they just change that shape a little bit. And as I was not sure if I can transmit videos. These are just the images. So if you have two droplets, the only thing you do here is switching on the lamp. You see that the droplets coalesce, and at the same time you get the imbibition. And I cannot go into details with this, but this is what you see then is the imbibition ring, and this gives you a clear indication that water is going into the film. So this is important. What's a water imbibition and contact angle transition or wetting transition? And one project about local functionalization, this was a collaboration with Nicolas Vogel in Erlangen, who was postdoc in the Eisenberg group. So he is an expert in doing these inverse monolayers and inverse opals. And the nice thing about these porous structures is that you can tune the opening angle. So you just deposit polystyrene particles, you fill the interstitials, and depending on how much you fill them, you tune this opening angle. And this, you can imagine if you see the images, strongly influences roughness and with this wettability and the contact angle. And we were just asking, yeah, this is the just theory behind. So this is nothing of our data, it's just the principle published by the Eisenberg group. And Nicolas Vogel's group can just prepare these samples. You see SEM images here. This is how they look like. They are nicely colored due to the reflection colors. And our idea was they can do this with gold. So they can deposit gold on top, gold at the bottom. And again, you have nanoscale gold structures. These are plasmonically active. And you can tune the wettability. So our first approach was, okay, can we do 3 functions in a pore? And how to do this? So you have to use not just surface chemistry, because you have silica here, gold here, gold here. You have to discriminate as well between the inside the pores and outside the pores. And this you can do, was our hope, using wettability. Yeah. So what we tried is to get an initiator for ring opening polymer metathesis polymerization here to the silica wall, to use a solvent that penetrates the pores for this, and then use a polymer that makes the pores even more hydrophobic due to its function. Then use water to deposit something on top of here, because in a wetting state where the water does not penetrate the pore, and then change the solvent to a solvent that penetrates the pores, and then functionalize the gold at the bottom. And just to guide you through, we did the first step with a ring opening metathesis polymerization. These are SEM images. You do not get perfectly nicely filled pores with something like a curtain of polymer, but you see here that in vacuum you have these lines, which is polymer. You see this in the infrared spectra, and you nicely see this in the wettability as well in the contact angle. Then you just use this wettability, you deposit a droplet of water, and this is a little bit the trick to get the right thiols that are not just transferring through vapor phase and that are just sufficiently soluble in water. So probably not an ideal monolayer neither, but nevertheless, we could show that we see these sulfur peaks and the nitrogen of the thiols. So it seems that there is a functionalization on the gold. And if then you switch the solvent to ethanol, you can just deposit gold on the bottom of the pore and then do an ATRP polymerization. That's quite tricky to show, because even using XPS, you are not going completely into the pores. So the signals are always quite small because you have gold here. The IR spectra look a little bit weird, but nevertheless, you see small thickness of this polymer here. And we use just complementary elements, so bromium here, so that you can get a kind of idea that you have really 3 different functions into these pores. So this was the first approach. Yeah, just giving you the final summary of the functions that we placed. And then the second one, which I should mention this, and the group of Nicolas Vogel was looking at the plasmonic part and what they saw as well. So if you ask what should this be good for, if you change these size ranges of the whole structure here on top and the disk structure on the bottom, you get, of course, coupling of these plasmons. And what they observed, that they get a new hybrid band here. And this is especially sensitive to what you place here in the silica pore walls. So yeah, we finished this project and we have the follow-up project under evaluation. Let's see if we will get money to continue the sensing part a little bit. And the last aspect, which I mentioned, I already placed in my application for Darmstadt, and then for a long time, I didn't get funding until I got the ERC. For this idea was use the surface plasmons of metal nanoparticles or just planar gold substrates and use the surface plasmon just as the light to initiate polymerization. There are some problems behind, because first, the surface plasmon on planar gold surface, they are usually in the, let's say, 450 to 700 nanometer range. For the particles, even worse. I think the best is the spherical particles that you can tune a little bit. If you go to more advanced particles, you go to the near IR as well. So everything gets more complicated because photopolymerizations are usually initiated in the UV. So the first thing is you have to do is to get your chemistry synchronized with the irradiation wavelength. And we tried this on planar surfaces first, and then we came up with just introducing these gold particles in between the mesoporous films. And this worked more easily because I think the detection is slightly more easy, although it's still complicated. And you might know the work of Zopera, who did this on just particles, and they use just AFM to see the nanoscale diameter changes of the particles. But if you introduce the particles into the films, of course, you cannot access them anymore. So everything gets a bit more complicated. And the chemistry we chose at the beginning, and that's a vital field in polymer chemistry, I would say, visible light-induced polymerizations, are dye-sensitized polymerizations. This was our first proof of concept. And they are nice. They are not very controlled, not a very nice mechanism. But the nice thing about this is that you can just change the dyes. And I mean, you have a lot of dyes covering the entire visible light wavelengths. So this was our first solution to that problem. It's quite complex in terms of mechanism. You excite the dye. I think Zopera proposed the mechanism in 2011. You excite the dye, you transfer an electron from the triplet state to this co-initiator, and then here you start the polymerization. So it's quite dirty, I would say, in terms of chemistry, but it works. And what we showed, and then we continued now with the chemistry development, and this is as well a PhD thesis going on, just taking all these recipes from the literature that now develop in terms of visible light and controlled polymerization, and now the chemistry gets a little bit more defined. And what I would like to share with you is that I think this year or last year proved with the particles that very probably taking all our analytics together, we are able to nanoscopically around such a particle build kind of polymer, and then you can of course look at the sensitivity of the plasmon band shift 2 and think about sensing. We could do this with a Iniferter-based polymerization, visible light Iniferters in a grafting through approach at the beginning. I think you can take grafting from as well, and this depends strongly on the chemistry that you can realize in these systems. And you see in the IR spectra that if you just irradiate, you get a large polymer band. And then, of course, you have to irradiate with an intensity that does not just start solution polymerization, but only the plasmons then irradiate. And then, of course, your CO vibrational bands are much smaller, and the shift in the plasmons is as well. I think this was the last thing that I wanted to share. So in conclusion, I think we did some steps starting from a Schlenk line in Buenos Aires, looking at interfacial and physical phenomena, and try to reflect on how you could use this for synthesis in terms of wetting or even plasmonics, or just using printing techniques to get smaller film thicknesses and combine this with more advanced polymer chemistry. And of course, I have to thank my group and all these funding partners, because without this, I would not have even had one PhD student. And of course, thank you for the invitation, which is, again, really an honor and a pleasure. And I'm looking forward to the discussion.
Thank you very much, Annette. It's incredible what you have done in 10 years.
Well, my PhD students, I'm stuck to my desk, I think, most of the time.
Well, now, you know that's not true. They do a lot, but also you So thank you again. And this is really, really interesting. I give room for the audience to ask any question. Okay.
Can I
Galo,
make a question?
now, yes, of course.
Hi, nice to meet you, Annette. I really enjoyed your beautiful works. And I'm interested in the modification of the polymers. Can you control the density of the modification of polymer from the top of film to the bottom of film?
And this is exactly, I mean, in terms of the density from one side to the other side, making a gradient in density. This is exactly the idea behind this plasmon work, because we started from a planar surface, and then you would say the intensity of the plasmonic field is exponentially decaying from the bottom to the top. And as we know that the energy is just influencing the polymer amount or the chain length, depending on the mechanism, or the grafting density, this should be possible. So I would say with the last slides I showed, we are on the very first steps. But even if we would achieve this, the problem characterizing this would remain. So I think that this is the way to go. But even if we would get the synthesis into that direction, I would not be sure what would be the limitation in characterization. So maybe this EDX scanning would be the best, but still there you see not just a chain length, because I imagine if I see the papers from i-Opal and the size ranges that they do gradients like this doors, for example. I mean, if you translate this into a gyration radius of polymers, I mean, you are really like in two chains of having 10 monomers, two more chains having 8 monomers, if you want to make this gradients. So I'm still reflecting on what could be possible to do this. And this would be, of course, very cool if you can do that. But yeah, let's see what the future brings. To now, what you can do, I think the most realistic one is you make this layer-wise design. Then you could say, okay, with the gravure printing, you can fairly do like 15, 20 nanometer thickness of layers, and you bring different polymer densities in these layers. I think this is something that is realistic to do in the next years. But to do what i-Opal is simulating, I think there has to be another concept to approach this to prove the control.
Yeah, that's cool, because if we can prepare that kind of structure, there is a chemical potential gradient. So
exactly.
Maybe ions feel that potential, then we can enhance the diffusion of the ions.
That's exactly the idea. Because if you think of biopores, I mean, you can be selective, gated, directed, and the direction part is the idea. And then, of course, if you want to do this with ions, not with larger cargos, you could think about larger cargos. But if you want to do this with ions, you have to be in the size range of the ions. And then you have to do this like two chains, maybe. I imagine it like this. If you think about larger pores and particle transport, then maybe it's more realistic, because then you could make the gradient in larger dimensions.
Yeah, understand. Thanks so much.
Yeah, welcome.
We have a question from Paula in the chat, because she don't have camera and microphone, but I will read it for you. First, she says, thanks, Annette, for the talk. I would like to know if you have tested using other kind of metallic nanoparticles to tune the light absorption, like rods or stars that absorb at 600, 800 nanometers, which was my question too. So thank you, Paula.
Yeah, I mean, we are not experts in these particles, so we would not have, of course, I had that idea, but I would not have started that project. But how life sometimes plays, I had an application of a very talented postdoc that was just into these particles, and she was just desperately searching for something in Darmstadt because her husband found a job here. So I said, okay, I don't have a job, but if we can try to get a fellowship, and one of her things is doing this. So she was trying, or she's trying right now, I think, diamonds and rods. We are still playing around with this because if you place them into this normal salt gel film preparation treatment with the acid and the high temperatures, we see basically that these particles lose their shape. So there are rearrangement, reformation things going on. So we have to completely adapt the preparation mechanism probably. But this is something she's doing. So I would not say that I'm doing this because I think it's a little bit of her baby, and I'm not too much into these particle details. But these are the first steps that we are using. But of course, I would be more than happy to continue this part with other advanced particle fabrications. And of course, I know, Paula, even if we did not cross, because I think you were in Spain when I was in Buenos Aires, I'm aware of the plasmonic parts, and I think that's in very many senses very, very interesting too. Yeah.
Excellent. Well, Galo had raised a hand a long time ago, so.
Thank you. I'm very proud of what you achieved. Really, I have to say it. So congratulations, first of all. Second, I was interested in your in the structure of your device with the gold nanoparticles. Why did you locate the particles in the center? Because you wanted to put more polymer in near the center, or
this was really the proof of concept. It was starting from the frustration that we had with the planar systems, because that's what we started, and just taking really an SBR equipment and go in there, and then depending on the wavelengths, we have to change from gold to silver. We had really difficulties to prove the nano-local limitation. And then at some point, we just tried, okay, let's try the particles. We just had a recipe of gold, silver, alloy nanoparticles and gold particles. Let's just try this. And as the synthesis somehow worked, we just deposited the same film. We did not change the recipe or the dip coating speed. So of course, the question now is, if we continue this, especially with Rahele, this postdoc that I mentioned, is of course to think about in the ERC a little bit about the design, what you want to achieve, and the polymer density too, because here, of course, if you look at transport, you only have small parts of the pores with the nanoscale polymer film. So this is something that we still have to sort out. So we do not have the transport demonstrator yet, because we were struggling for, I think now 4 years to really get the proof that this can be nano-local. Yeah. So we didn't care, is the answer at that point. And we will try to care. We will start to care in the next years. Yeah.
An alternative view is just make a control reduction and have gold everywhere, and you can then either wash or make a galvanic displacement or something.
Yeah, that's true. Yeah, this is something you could try as well. Yeah, and I mean the strategy that I saw in your group as well, that you do the particles in the pores. I mean, you can think about a lot of demonstrators then in terms of transport, but we were just struggling so hard to get the chemistry combined with the particles and the plasmons at least in any way. So
it's not evident.
Yeah.
Any more questions? Sorry, I was just thinking. Have you thought, okay, I have one, on using like 2 photons absorption, using plasmon resonance, but 2 photon absorption to tune the wavelengths?
Yeah, just theoretically,
Okay.
because, well, very simple, I just don't have the equipment close. And then you could think, of course, as well, if you go into that direction, in using like everything that's developing in the printing field, right? If you use, if you think about the two photon stuff, and developing, or in the microscopy field, developing this further. So I think there is no theoretical reason that it should not work, but I cannot give any kind of data on that. Yeah.
Okay. Yeah, maybe you need power sources. Like
exactly. Yeah.
Lasers.
Yeah, exactly.
But, yeah.
Or maybe even pulse lasers. So yeah, to get the statistics. Yeah, that's right. Yeah. So we don't have this here. So yeah, we didn't try this.
We can think of something to collaborate on that matter if you are interested.
Yeah, for sure. Yeah.
Right.
Because then you can really write. So what we do is, I mean, beyond the plasmons, we think in the direction of high resolution microscopy techniques. I call this polymer writing, so nanoscale polymer writing. So this is actually the further development that we try in the ERC, and to get a bit into this nanofabrication stuff. Right. So this is something that we try, but the two photons we didn't approach yet. Yeah.
Okay. Well, there is any more questions? Well, if not, we thank you again, Annette. It's impressive.
Very, very welcome.
and a pleasure to have you here. So
yeah. I hope that times change so we can meet again in Buenos Aires at some point.
Yes.
Or exchange students. That would be very cool as well.
Yes, hopefully.
So yeah.
When this is end, we can think something.
Omar is in YouTube watching.
Oh, okay.
Hi, Omar.
He was he was very happy to see you here.
Very cool. And I just see this, you wrote this, Carlo, with X reflectometry. Yeah, exactly. So if we, I mean, this was an idea, I think, of Matthias, who actually did this, who wanted to come to Buenos Aires, and then I think the DRD just didn't give the funding, and then yeah, he was going to the end. So it's just, yeah, if you have ideas on this, I would be more than happy to continue that part. Yeah. So we were definitely follow this nanoscale stuff. So I think if COVID is a bit more under control, I will for sure approach you on this. Yeah.
He's sending a big hug by WhatsApp.
Well, thank you.
Got really excited about this to make a common projects in the framework of a collaborative project. It's very nice.
Yeah, that would be cool. I mean, any idea that's going around there, I would be very happy to get this a little bit active again. I think now, as we are settled somehow, that we have some things that are stable and developed, and I'm stable over here, so that's I think a good point to start something. Yeah.
And I wanted to say that you have a record in our laboratory.
Why? In breaking Schlenk lines? No.
No, you published your first paper before getting your first payment.
Yeah, that's yeah. I mean, there are a lot of these nice stories that were coming back to me as well. That's the salt in my life. Yeah, it's
we
cool.
told this to that bureaucrat in the elevator. You remember when we went to the
Yeah. I remember how we went to the ministry, and I don't tell anybody where you place my salary to pick it up.
Remember? Oh my God.
Okay, I'm stopping the YouTube transmission because
maybe
something. So bye.